Hello, my name is Will Kleber, and today I will talk about automated code repair to ensure spatial memory safety. The problem that this project addresses is that software vulnerabilities constitute a major growing threat. Spatial memory violations, such as buffer overflows, are among the most common and most severe types of vulnerabilities. In recent years, memory violations have constituted 15% of vulnerabilities in the NIST National Vulnerability Database and 24% of critical severity vulnerabilities. In 2019, a memory vulnerability was discovered in the iPhone iOS. It allowed an attacker to remotely take control of the phone when the user visited a malicious website. This vulnerability was exploited by the Chinese government, according to TechCrunch. A similar vulnerability was found in the Android stagefright library in 2015. It allowed an attacker to remotely take control of a phone by sending a vulnerable phone a specially crafted MMS message. Our solution to this problem is to automatically repair source code to assure spatial memory safety. Our technique will insert code to abort the program or call an error handling routine immediately before a memory violation would occur. This prevents an attacker from being able to exploit the program. In our approach, we transform the source code to an intermediate representation, an IR, while retaining a mapping back from the IR to the original source code. We then repair the program to use fat pointers to track bounds of pointers and to insert a bounds check before every memory access. We then translate the repairs that were done at the IR level back to source code. Viewed as a black box, our ACR tool takes as input a buildable codebase written in C, and as output, it gives you back repaired source code that is still human readable and maintainable. We envision that our tool can be used both for legacy code and as a tool in a DevOps toolchain for new code. So, why would you want to do repair at the source code level instead of doing it as a compiler pass? One reason is that repair at the source code level is easily audited, whereas with a compiler pass, you kind of have to trust the tool. Secondly, repairs at the source code level can easily be tweaked to improve performance if necessary. Third, repairs that are done as a compiler pass involve a change to the build process, which is generally more difficult and more error-prone than changing the source code, and it can create unwanted dependencies. Fourth, with repair to the source code, it is okay to do a slow, heavyweight static analysis because it produces a persistent artifact instead of needing to be done during every single build. Here we see the repair pipeline used by our tool. In step 1, we parse the original source code into an abstract syntax tree, an AST, but we also maintain a mapping back from the AST to the original source code text. In step 2, we translate the AST to an intermediate representation, an IR. And again, we retain a mapping from the IR back to the AST. In step 3, we perform analysis and repair at the IR level. Then in step 4, we map the repaired IR back to AST, and in step 5, we map the repaired AST back to source. So if a AST node is unmodified, then we simply reuse the existing source code text. Of course, if an AST node is modified, then we have to regenerate source code text. We replace row pointers with fat pointers. A fat pointer is just a struct that includes the pointer itself as well as bounds information. So before dereferencing a fat pointer, a bounds check is performed. For each fat pointer type, we introduce a corresponding fat pointer type defined as follows. A fat pointer type is a struct with 3 fields: the row pointer itself, the base of the memory region, and the size of the memory region in bytes. Fattening of pointers has previously been performed as a compiler pass, and in this work, we extend it to do the repair at the source code level. Consider an example program with a pointer p that points inside of a string. In our repair, we convert P to be a fat pointer. In addition to the original pointer, we also have a pointer to the beginning of the memory region and another pointer to the end of the memory region. Here we see an example code snippet and the repairs that our tool makes. On line 7, our tool changes the char pointer to be a fat pointer, and it changes the call to malloc to instead call fat malloc, which is a wrapper around malloc. On line 10, we insert a bounds check before the pointer dereference, and on line 11, we change the raw pointer arithmetic to instead call a function that does the pointer arithmetic on fat pointers. For each pointer type, we define a wrapper around malloc, and if malloc returns null, then the return fat pointer has a size of 0. For each fat pointer type t, we introduce a function fatpadd that performs pointer arithmetic on that fat pointer type. Alternatively, we can define a single macro that works for all fat pointer types, and this requires the use of widely supported GCC extensions to the C language. Now I would like to talk some more about how we map changes that were done at the AST level back to the original source code text. So we implemented a modification to Clang to extract a mapping between the source code and the AST. In translating repairs that were done on the AST back to the original source code text, the C preprocessor is the main source of difficulty. So if we need to make a repair to a macro use, what we do is we just expand the macro and repair the expansion. If a repair needs to be done to pound included code, then we just repair the file that was pound included. If a conditional compilation directive, such as pound ifdef or pound endef, occurs inside of an expression, then we just need to be careful not to clobber that directive. When an expression or a statement is repaired, we generate new source code text for the repaired portion of the AST. For unchanged portions of the AST, we reuse the existing source code text. Our ACR tool is implemented mostly in Python, and it uses a modified version of Clang. Our research questions include, can our repair technique guarantee memory safety, and what is the performance overhead of the repair? We ran our tool on 52 memory safety benchmarks from SVComp. To verify the efficacy of our repairs, we ran Symbiotic, which is a software verification tool, on both the original and the repaired files. So on the original files, Symbiotic was unable to prove that any of them were safe, and it was able to prove that 48 of them were unsafe. And on 4 of them, it was unable to determine memory safety. On the repaired files, Symbiotic was able to prove that 27 of them were safe, and it was unable to prove that any were unsafe. On 25 of the repaired files, Symbiotic was unable to determine safety. To measure the memory overhead of our repairs, we tested our repair tool on a selection of benchmarks from Spec 2006. As you can see, the memory overheads are kind of high. For bzip2, for example, we have a runtime overhead of 64%. So can we reduce this overhead? Yes, by repairing only the suspicious locations. So in particular, we run a static analysis tool, and then we insert bound checks only for those memory accesses that were flagged by the static analyzer. This considerably reduces the runtime overhead for most of the programs. So for example, for libquantum, we have a runtime overhead of 3%, 9% for sgen, and 3% for bzip2. However, MCF still has a 62% overhead, and that's because MCF makes extensive uses of linked lists. And currently, we still fatten all pointers, even if we never use the bounds information to insert bounds checks. as future work on this project, we intend to change that so that we only fatten those pointers that we actually need to fatten in order to preserve the bounds information for bounds checks that we actually insert. We cannot guarantee memory safety in the presence of non-standard pointer tricks, such as XOR linked lists, reuse of memory for different types, concurrency, because race conditions can cause memory corruption, and external code that accesses program memory. If the program's data structures are accessed by external binary code, then pointers inside of them cannot be fattened because that external binary code, it relies on the program having a specific memory layout, and if we fatten the pointers, it'll change that memory layout, and that will break the external binary code. And we can identify those pointers using a whole program points to analysis with an allocation site abstraction. In conclusion, our tool repairs code bases to ensure memory safety by using fat pointers. The user can select one of two modes of operation. First, to make all possible automatic repairs, which incurs a larger runtime overhead. And second, to repair only the likely memory violations, which incurs a significantly less runtime overhead. Our tool will be available on the SEI GitHub site. And this is a research-grade tool. It's not a production-grade tool. It does not work robustly on all real-world C programs. But in the long term, and with further development, we do hope that this technology will be able to be used to ensure memory safety as part of software projects with code written in unsafe languages such as C or C++. Thank you for your time.
Hello.
Hello.
Yeah, so if you have any questions, please leave them in the comments. Well, actually, I have one question. So my question is, this kind of repair that you generate, are they intended to be later used and modified by the developers, or they are just applied once before the compilation as a kind of separate step, the single
Yes.
step?
So they are intended to be able to be changed by the developers. So we do try to produce the code that is maintainable. So you can take these changes and commit them to the repository, for example. So it's not just like you repair it and then you immediately compile it and throw away the changes. That's not what we're doing. We do intend these changes to be persistent. Now, I guess in some cases that might not work. So if you have a lot of macros and we need to make repairs to the definitions of the macros, we currently can't do that. So what we do instead is expand the macro and repair the expansion. So in that case, you might not want to keep the repair, but except in that case, we do intend for these repairs to be persistent, that you could keep them and have the developer modify them, maybe tweak them for performance and so on.
Thank you. So there are some other questions from the audience. Is it always possible to map the IR back to AST? Are there challenges in this stage?
Okay. So for that, in our particular case, yes, the way that we have designed the IR and the AST allows us to always map the IR back to the AST for the particular types of repairs that we make. Of course, in the general case, that might not be true. So if you want to try to do a different repair than the types of repairs that we do, you might run into the case where you cannot map it back. But for the particular types of repairs that we do, we are always able to map the changes at the IR level back to the AST.
And the second question from the same person: how do you know if you should exit the program or insert a error handling code, and which one?
Okay, good question. So right now we it's set up by default to always have the program abort. Now, if the program does have some way of handling that error, then we would be able to modify the repair so that it uses so that it jumps to that error handling routine instead of aborting. And what that would be is just to replace the part where it aborts with instead to have it jump to the error handling routine. And currently that is very manual. That we don't really have any automatic way of doing that. But in principle, you could develop something that's a little bit more intelligent than what we do right now.
Thank you. And the next question: how to prevent assess code regression when making correction on IR level?
Let's see. Okay, I'm not completely sure what is meant by a regression in this case with respect to going back and forth from the IR level. So how do you prevent or assess regression when? So I mean I would say that it definitely does. Our technique definitely depends on us making intelligent choices of how we represent the AST and the IR. We have designed the IR to work very well with the repairs that we make. So if you're going to do a different type of repair, you might design the IR differently. So I think that's that. So our technique is kind of sensitive to the type of IR that you use, at least if you want everything to work smoothly.
Thank you. So the next question is, apart from memory safety vulnerabilities, what are other kind of vulnerabilities that you think you can be automatically fixed in this way effectively?
Okay, that's a good question. And I guess the memory vulnerabilities are an easy way. I guess one thing that makes them easy is that being able to exploit a memory vulnerability is really bad. So what we can do is instead of we can repair it just by aborting the program, and that would be a huge improvement. Whereas if you have a different type of mistake that isn't such a huge security vulnerability, just aborting the program or calling some global error handling routine might not be so great. So I guess that's one limitation on the types of repairs that this can make, is that unless you know how to repair it intelligently, unless there's a clear pattern of what to do, it can be difficult to make other types of repairs. Now there are, I guess, some cases where maybe if there's again off by one error and you can detect that, you might be able to fix that. For example, that's something that if you can detect with high confidence that this really isn't off by one error, then you might be able to just automatically fix that error. So I would say, in general, the types of vulnerabilities that can be fixed automatically, you have to be able to, with very high confidence, classify that it is an error, and you also need to know with high confidence what a reasonable or acceptable solution would be. Now, with memory errors, of course, it's very clear when an error would occur. It's where the memory access would be out of bounds, and it's also very clear how to fix it. In our case, we just abort the program. I would say that it is harder for other types of errors, but there probably are some other types of errors that we could also address.
Thank you. So we currently have around 40 seconds, and the question that we have is if the first repair attempt fails to pass the verification pass, can your tool consider the feedback info to further refine the patch?
That's a good question. Currently, our tool is not able to do that, but that is something that we can look into for future work, being able to see if it doesn't pass, what some things that we can do better to try to make it work better. So that is definitely something that we could pursue as future work.
Well, we have only just a few seconds, so thank you very much for the questions and for the answers, and you can continue discussion in the